Great. Thank you so much, Greg, for the introduction, and thank you all for having me. So I'm really excited to be talking to you today about soft and continuum robots for unstructured environments. So let me start by talking about what I mean by unstructured environments. So here are some examples of environments that are outside of like a structured environment like you would find in the factory. These are environments where we would like to have robots that are able to operate here. So on the top left here, we've got a underwater archaeological site where we might want to send a robot in and explore this delicate structure without damaging it. Over here, we've got a collapsed building where we might want to send in a robot and either look for trapped victims or even help rescue them. Down here, we've got a surgical scenario where maybe we want to send a robot inside of the human body to try and either take video or take samples. And then over here, we've got a person playing tennis, and if you wanted to build a robot that could help their movements, that's also an unstructured environment as well. And I want to talk about what soft and continuum robots are. So these are some of the soft and continuum robots that I'm going to be talking about today. A soft robot is a robot made of soft materials, and a continuum robot is a robot that bends along its entire body as opposed to having discrete joints like the robots you might see commonly on a factory floor. So those are these. I'll be talking more about these in a minute. And the key point of my talk is that soft and continuum robots have an immense potential to assist humans with navigation and manipulation in unstructured environments. So hopefully by the end of this talk, I will have shown you some examples of why this is true. So I want to introduce another key theme that I'm going to talk about through the rest of the talk, and that's a couple of key themes. One is bioinspiration, and the other one is embodied intelligence. So bioinspiration is this idea that we often look to nature to help us come up with inspiration for building both the design and the control of our robots. And so looking to nature, these are some organisms that we can look at that have inspired some of my work. So here's a natural vine, and it's able to grow in order to both support its body as it grows along this fence, and then it can also kind of grow to weave its way through the fence if it wanted to go through it. Here we've got a spider monkey where it's got this amazing body, including its tail, where with its tail it's able to do things where it's very strong, but also it can adapt to a bunch of different tasks. Because the tail is long and thin, it can get into small spaces, but because it can actually grasp with its whole body, it can allow the monkey to wrap around a wide variety of different sizes and shapes of objects. And then over here, we've got an amoeba, which is at a much smaller scale, but it has a fully soft body, and it actually kind of morphs its shape in order to navigate its environment. So that brings me to this idea of embodied intelligence, which is this idea that when you're thinking about designing and controlling a robot, you can put a lot of intelligence in its brain and in its control algorithms, or you can think about trying to design the body of the robot so that you don't need as complex control. And so a lot of these natural structures have an intelligent design of their body that allows them to do the tasks that they are designed for. So we're gonna talk about that a bit more with some of the projects that I'm gonna show. All right, so the outline of the rest of my talk is I'm gonna spend about the first half talking about some work on vine-inspired growing robots, and then I'll talk about 2 projects on other bio-inspired robots that we're working on, and then I'll finish by talking about some wearable robots. All right, so before I start, though, I want to kind of just do a shout out to my lab. So I lead the Notre Dame Innovative Robotics and Interactive Systems, or IRIS lab. And we chose the name because at Notre Dame, our mascot is the Fighting Irish. And so this way we could say, go Irish and go Iris. And so the things that we work on are robot design and modeling, especially right now for inflatable robots and continuum robots. Then we also work on human in the loop control, so thinking about how a person could teleoperate a robot to go into a confined space, or how a person could wear a robot in an intuitive way. And we're working towards human-centered applications, and the main two we're working on right now are robots that go into confined spaces that people can't go into, and also interacting with the human body. And these are the graduate students and undergraduate students who are in my research lab this semester. And you'll be seeing some of their work as I go on. All right, so let me start by talking about vine-inspired growing robots. And I'm going to begin by doing a little bit of background on vine robots, and then talking about a vine robot field deployment that I participated in as a PhD student. All right, so this is a vine robot eversion principle, where it's a vine robot is made of a tube of flexible material that is airtight, and it's folded inside of itself, so that it will come out from its tip. I actually forgot to get out my demo. I do have a demo. Wanted to show you. I keep it in my purse all the time. It was my simple vine robot demo. Let me just show it to you really quick here. All right, so here's my vine robot that I carry around in my purse, and it's basically it's plastic bag material. I'm gonna blow into it a little bit so I can fold it inside out. All right, so here it is. I'm folding it inside of itself, similar to what you do when you fold a pair of socks or something. And when you have it all the way inverted inside of itself, it's very short in length. And then if you inflate it, it'll come out and extend from the tip. Okay, so there you go. That's the demo of the vine robot. And you can see this is it's a very simple to make thing. This is a very simple version of it that has no sensors and no actuation to steer it. No, and we can also make it out of a much more durable material if you'd like, but it's the basic concept. And one of the things that you'll notice is that as the pieces come out of it, the part that has grown out doesn't slide relative to the environment. So like these black and red and black lines stay where they are, and the new material is added at the tip. And that actually makes these really good at navigating a lot of confined spaces. So here's a video showing one of the longest, actually the longest vine robot that has been deployed so far. It grows out of this spool where it's got a bunch of materials stored in it. And then it grew around our entire lab at Stanford, our entire building at Stanford. It grew to 72 meters long. And the only reason it stopped growing was because there wasn't more material on the spool to allow it to keep going. So these robots are capable of enormous length change. They're also really good at growing through confined spaces, and even spaces that are smaller than their own diameter. So here's a vine robot that grows through a rectangular gap that is 1/8 of the height of its diameter, and it's able to just kind of feed its way through and then keep growing after it has gone through the aperture. Similarly, these robots can passively adapt to their environment, similar to how natural vines do, where this one is not actively being steered, but it is able to run into the obstacles in the environment and just keep going, because it both extends from the tip and because it's soft and hollow and inside. So this is a project that I worked on during grad school. If you're here in person, you can't really see all the other people who have worked on it, but it's a collaboration with many other people from Stanford and from KAIST and from UC Santa Barbara. But we built this teleoperated steerable vine robot. Let me restart the video here. We built it so that we could deploy it in the field. And it's made of this durable fabric material, and it carries a camera on the end. And it's steerable with a joystick. So we built it in this base that has a motorized spool that allows us to control how fast the material comes out of the tip. And then it also has these series pouch motor actuators on the side that allow us to steer it left and right using a joystick. And we also put a camera on the end of the robot that is pushed along by a cap. And it's a wired camera, and the wire gets pulled into this zipper pocket, and there's a zipper on the cap that zips it up so that the wire doesn't get stuck on the environment. And we had this amazing opportunity to deploy it in this robot in the field in Peru at an archaeological site where there are these underground tunnels that were built by the people who lived there between 1500 and 500 BC. And these tunnels are about a foot wide, and so too small for a person to go in. They've got rocks in them, so they're challenging for a wheeled robot to navigate through. And we successfully deployed the Viner bot in 3 of these tunnels and took video that we gave to the archaeology team to show them what was in there. We didn't actually find anything super interesting, although someone else who was deploying a robot in a tunnel next to the one I was in found a really old vase, which was pretty awesome. But this was a really cool demo of the Viner bot technology and its ability to be useful practically in the field. So some of the takeaways from this Viner bot field deployment were that Viner bots are practically useful for exploring confined spaces in the field, and also that this embodied intelligence, so their desirable unactuated behaviors where they kind of bounce off the environment, makes the control relatively simple. We just had a simple teleoperation algorithm that allowed us to control them over these complex terrains. And this field deployment also highlighted some future directions for research where we'd love to be able to enable Viner bots to do more challenging tasks. So what are those more challenging tasks? One of them is confined space mapping. So on this robot that we deployed in the field, the only sensor it had on it was a camera at the tip, and it was not super intuitive as a human operator to know where the robot had gone just by looking at the tip camera image. And so it would be great if we had the ability to map where the robot had gone, and we could use that to even map out the spaces that it's exploring. Another thing that we'd love to be able to do is to make these robots not just look in the environment they're growing through, but also to manipulate and grasp things in the environment. So this is a potential scenario where maybe there's a person who's trapped under a pile of rocks, and you could have a Viner bot mounted to a mobile platform, maybe a quadrotor or something, and it could wrap around an object and then uplift it off the person. And this motivates actually some of our work on Viner bot force sensing that I'll talk about. And then finally, we'd love to be able to get these Viner bots to be able to navigate not just confined spaces like the ones in the tunnel here, where their body is fully supported by their environment, but spaces more like this one, or like the rubble field that I showed earlier, where you have combined free space and confined space that you'd like to navigate. So this motivates some of our work on Viner bot 3D shape formation and modeling of that. All right, so that was our kind of intro to Viner bots and the discussion of Viner bot field deployment. And now I'm going to talk about our work on Viner bot shape sensing. So this is our work on fiber optic shape sensing for Viner bots, and this is led by my undergraduate student Kabir and my PhD student Sierra. And we're working with this technology called optical frequency domain reflectometry, or OFDR. It's similar to fiber Bragg gratings, if you are familiar with those, but it allows you to get discrete measurements of strain along a fiber at every 0.65 millimeters along it, which is quite amazing. And so we buy this interrogator from a company called Luna Technologies, and it sends light down a fiber, and then based on how the light reflects back, it's able to determine the strain along the fiber. And what we're interested in doing is putting bundles of fibers together so that based on knowing the strain measurement along each fiber, we can actually back out the full shape of the fiber. And then our idea would be to put this onto a Viner bot. So this is like a cross section of a Viner bot. This has previously been shown with this Luna system to have shape sensing accuracy of about 1 to 2% of the length. However, that technology of how they did that is proprietary, so we're kind of we had to build our own version of it to try it out on binder bots. So what we ended up doing, we need to fabricate these sensors out of 3 fibers. And so we put together these sensor fabrication rigs where we 3D printed the outside of these rigs, and then the inside we needed a very precise triangular shape like this that could hold the 3 fibers together. And so we actually cut them with a femtosecond laser cutter to get a really precise triangular hole that's the right size for these fibers. And then when we can put the fiber through these 2 successive holders and glue it with a strain gauge glue as we pull it through the fibers, and you can see here they start separately as 3 fibers and then they come out together as 1. And then so this is what it looks like once you create the fiber bundle. You can actually this is a reconstruction of the shape of the robot where, or sorry, of the fiber bundle, where I'm moving this around and you can see that we can plot the shape that it's bending to in real time, and it matches decently well. And we're actually still quantifying how accurate this is, but we put it on a binder bot, and in order to do that, we needed to put some protective tubing around the fiber bundle to prevent it from bending to too tight of a radius of curvature. And then we can just tape or attach the protective tubing onto the outside of the binder bot. And we did a demonstration here that you can grow the binder bot through this maze. This is 3 time points in a growth sequence where the sensor starts folded back inside the robot, and then it deploys out as the robot grows. And you can see that here the shape of the sensor at least roughly matches the shape of the robot. And we're still working on quantifying the accuracy of this and really nailing down how to do the calibration of this sensor so that we can get the true shape with enough accuracy to do the tasks that we would like. But so key takeaways from this project are that optical fiber shape sensing is promising for binder bots. And some of the benefits of this type of shape sensing are that the sensors are flexible, so they can kind of sense the full shape of this really infinite degree of freedom soft system. They're super high resolution. We've got data every less than a millimeter, and the wiring is really simple because we don't actually need any other wires in separately from the fibers themselves in order to sense the robot shape. And some of the future directions based on this work are we're excited now that we have this capability to sense the shape of the robot. What are some of the new capabilities that we can do with binder bots? For example, mapping the spaces that they grow into, or maybe doing some more complicated autonomous control. And okay, so that's our work on binder bot shape sensing. Now I want to talk about our work on binder bot force sensing. So this is a project that is led by my undergrad student Michael, as well as my PhD student Sierra. And with this project, we were interested in this is kind of working towards the goal of making binder bots able to manipulate objects in their environment by wrapping around them. And we would love to be able to sense the contact forces that are exerted by the binder bot and use that in the control of the robot while it's also growing and steering. So this is our force sensing system that we developed here. The robot has 6 different force sensors around the outside of it, 3 on the left and 3 on the right. And here we're demonstrating just one of them being used in the control of the robot to steer the robot towards the force that's being applied. So this is what the air pocket force sensors look like that we've developed. They're just pockets of plastic bag material that's sealed at both ends with these exterior fold seals. And there's an air pressure sensor that's embedded inside the pocket. It's just glued in with an airtight seal. And then we have basically we've got a piece of tubing here so we can inflate the sensor, and then there's a cap so we can cap it off, and it has a constant volume or a constant amount of air in it, such that when you push on it, the pressure inside changes, and you can measure the pressure change with the pressure sensor inside of it, and that corresponds to an applied force. We also added these interior partial seals along the body of the sensor so that the whole structure would be flexible enough to mount on our soft vinyl robot. And we did several experiments to study the pressure change of these sensors versus the applied force. So we had, this is a sensor without the internal seals, and we put these weights of different mass on the sensor, and then measured the pressure change inside with different contact areas as well. And it turns out the increase in pressure is linear with the applied force, which is actually really great. It makes it easy to calibrate these sensors. But we did find that there was a small effect of the contact area, where when you have a really small contact area, but the same applied force, you end up with a higher change in pressure than when you have a larger contact area. And so this is something that we're working on, trying to mitigate the effect of, so that you could really trust the pressure reading and it'll map directly to the applied force reading. So this is a demo of the fact that we can use these sensors in the control of the robot while it's growing and steering. And here the robot's just showing its ability to sense the contact with this object, and it tries to curve towards it to try to wrap around it some more. Then it realizes with the next sensor that the object is too small for it to wrap around, and so it continues searching for an object to wrap around after that. All right, so some of the key takeaways for this project are that these air pocket force sensors are promising for vine robots, and some benefits of this technology is that it's inexpensive. It's just a plastic bag with a pressure sensor, and it's linear in sensitivity, which is exciting. And then the cool thing is that this technology is customizable in terms of you can make the sensor resolution whatever you want. You could scale up the sensors to cover a larger area per sensor. Or you can scale them down if you want to have a really high resolution. And some of the future directions that we want to do in this line of research are that we want to explore, again, the new capabilities that are enabled by force sensing. So we're excited about some of the trying to demonstrate the ability of vine robots to wrap around objects, as well as to kind of wrap around things like tree branches in their environment to support their weight as they continue climbing or growing. Yes, okay, so that's the end of our vine robot force sensing research, and now I want to talk about our vine robot collapse modeling research. So this is motivated by the idea, and this is led by my PhD student Syria. So this is motivated by the idea that we would love for vine robots to be able to navigate an environment like this, where the robot's body is not always supported by its environment, and we're trying to get from one side to the other. But unfortunately, the robot often collapses under its own weight when it gets long enough. And so we'd like to be able to model when this is going to happen, so that we can understand what are the parameters that we can vary to prevent it from happening. Or we could maybe sometimes we want the robot to collapse so that we can get down under something without needing steering actuation. So just having models for this would be helpful. So it turns out that varying the parameters of this robot can help the robot to go from one side to the other without collapsing. So on the top left is the original robot that I showed you on the previous slide. Here, we're launching it at a steeper launch angle. So it goes up steeper, and it turns out that it's able to grow longer before it eventually collapses. And it turns out it's long enough that it can actually reach over to the other side. And then similarly, here we're back to the original launch angle, but we've got a larger diameter, and the robot is able to navigate across this gap successfully. Because the larger diameter makes it stronger and stiffer when it's going over. And then finally, here we have higher pressure. So we have the original launch angle, the original diameter, but higher internal pressure allows it to go over the gap successfully. Okay, so we modeled this. We were interested to see whether a relatively basic model that just considers a moment balance on this robot would be sufficient to model how this behaves. So it turns out we take the moments that are exerted about this last point of support due to the weight of the robot. And then we equate them to the moment that is restoring the robot due to its internal pressure pushing at the tip of the robot. And it turns out that when you equate those, you can solve for the collapse length that you expect the robot to be able to grow to before it collapses for a given diameter, launch angle, thickness, density of the body material, gravity, and internal pressure. And turns out this model actually works decently well for straight robots. And so that's pretty exciting. So some of the key takeaways of this are that this moment balance predicts collapse length well for straight robots, and the collapse length actually varies non-linearly with launch angle as the square root of pressure and linearly with diameter. So one of the takeaways from this was that if you want to get the robot to cross this gap, probably the easiest way to get it to cross it is just to increase its diameter. And that's one of the most reliable ways to do that. And the other parameters are a little bit more iffy. And some of the future directions here are that we want to extend this model to arbitrary shaped actuated robots, so that we can do some 3D path planning and design for navigating a Vinerbot through a complex 3D environment. All right, so that's our Vinerbot collapse modeling research, and that's the end of what I wanted to say about bioinspired growing robots. So I'm going to talk now about some other bioinspired robots that we're working on in my lab. And I'll talk first about this spider monkey tail inspired robot. So this is a project that's led by that was led by a former undergraduate in my lab, as well as her name was Molly, as well as my PhD student Cataline. So I showed you the spider monkey earlier, and here's actually a video that we took at our local zoo near Notre Dame of a spider monkey swinging around in a tree. It's actually swinging from this tree branch using its tail. And the tail is truly an amazing example of what a continuum robot should do, or something that we would like it to be able to do, where it's really strong and it's able to support the full weight of the monkey, but it's also able to do some dexterous manipulation tasks, like it can reach under a fence and grab a peanut and pull it back. So this is the prototype of our robot, where we built a planar version of this tail, and we really wanted to demonstrate the ability to reach under something and grab something on the other side. So this is our tail that's reaching under this narrow passageway and grabbing the object on the other side and pulling it back. So the way that our tail works is that it's a sequence of 28 rigid vertebrae that are 3D printed, and in between each of the vertebrae, there's a pin joint that's surrounded by rubber of a certain stiffness, and then along the sides of the tail, there are cables that run along it that allow you to steer it in different directions. So we've got these different regions of the tail where we actually base this on the morphology of the real spider monkey tail, where it has the proximal region where it's stiffer and the vertebrae are larger. Then it has this middle region where it's less stiff with smaller vertebrae, and then finally it has this distal region with very small vertebrae, and it's the least stiff. And we also put a soft tail pad on the end of the tail, which matches the tail pad that is on the real spider monkey. And my student Molly played around with what's the right sequence of wires to put on this tail. This is what she settled on that made it look most similar to the real spider monkey. So she ended up having wires 1 and 5 that run from the base along the proximal region. Wire 2 runs from the base all the way along the proximal and middle region, and then wires 3 and 4 run from the base all the way to the tip of the tail. So one of the things that we noticed with this tail is that having this decreasing stiffness of the soft joints is important. So here's a version of the tail that doesn't have any of the rubber wrapped around the pin joints, and when you try to pull on the cables, it just kind of moves uncontrollably. But when you add these soft joints, now when you pull the cables that run along the full length of the robot, they move the robot tip first, and then if you pull them harder, they will move the whole rest of the robot as well. Another thing that we noticed is that this soft tail pad improves the grip. So here's a version of the robot without the soft tail pad, and you can just pull the object pretty easily out of its grasp. And then with the soft tail pad, it becomes a little bit more difficult to pull the object out of the grasp, and it also allows the robot to conform better to different shapes of objects. So some of the takeaways of this project are that this clever choice of relative stiffnesses along the length of the tail makes the control relatively simple. And this confined tail pad improves the grasping capability. And so some of the future directions are, we're actually working on, we have a 3D version of this tail that we're working with, that has, instead of pin joints, it has just rubber that allow it to bend in any direction. And we'd love to do more of the 3D manipulation and grasping that the real spider monkey is capable of. And then we're also working on static and dynamic modeling of this tail so that we can input a desired set of tasks that we would love for the tail to be able to do, and then output a design that has the appropriate stiffnesses and cable placement to be able to best do that task. All right, so that's our spider monkey tail inspired robot. Now I'm going to talk about our amoeba inspired robot. So this was led by a former undergrad in my lab, Nelson, and this is very similar to a vine robot in that it moves by turning its body inside out, but it doesn't actually extend in length. So this robot, we're calling it an everting toroidal robot, and it's just it's like a vine robot without a base that moves similar to a tank, but in 3D. So the way that it moves is it's got this propulsion device inside of it that's motorized. And we have this pair of motorized rollers that squeeze the inner material, which we call the tail, and they pull it this way, while these red passive rollers are grounded to the end of the robot body and provide a reaction force against which the active rollers can pull the membrane through. So this robot's really good at navigating similar types of spaces as a vine robot. So here it is shown navigating a maze where it doesn't have any active steering, but it's just propelling itself along, and it's able to conform to the shape of the maze on its own, similar to how a vine robot uses its embodied intelligence to navigate confined spaces. And then here's a video showing the robot climbing a pipe. And it turns out that we derived some equations that describe the torque that's needed at the motors in order to make the robot climb pipes at varying angles. And we did some experiments to validate the equations, and it turns out that with this robot, it was actually, it required the same amount of torque to climb up the pipe as to climb down the pipe, which we were surprised by. And the reason is because the main force that you have to overcome in order to propel the robot is the force that's needed to turn inside out the robot at the tip. And the weight of the robot is actually insignificant compared to that. So the cost of transport of this is very similar to if you were driving a wheeled robot that has a lot of friction at the wheels, and the friction dominates the whole system. So some of the takeaways here are that this robot, it has this kind of complex motion of turning its body inside out, but it still only requires this single control signal to move, which is really nice. And it moves equally easily at any angle because most of the force that it's overcoming is that eversion and inversion force. So in some of the future things we want to do are we're working on enabling active steering of this so that you can do a task like pipe inspection where you want to choose which pathway you're going down. And then we're also interested in miniaturizing this to go inside of the small intestine. The small intestine is 21 feet long, and there's no robot technology right now that's capable of getting inside of that really long tortuous pathway. And we think that this type of design could be really well suited for that. Yes. Okay, so that's our amoeba-inspired robot, and that's the end of our other bio-inspired robot section. So now lastly, I want to talk about a couple of our wearable robotics projects. And the first one I'm going to talk about is our body-powered prosthetic hand. So this is led by my undergraduate student Bona, as well as my PhD student Cataline. And the same type of structure that I just showed you, the everting toroidal amoeba-like structure, can also be used as a gripper. So this is actually an off-the-shelf water wiggler toy that you might have seen, where if you surround an object with it and then pull inward on the tail, it actually is able to pick up a wide variety of objects. And there have been a few papers on this idea over the last few years. And we were interested in seeing if this could be used as part of the human body to act as a prosthetic hand. So here's our design concept for our prosthetic hand. This is an able-bodied user wearing this device. And she's just grasping this handle. But you could imagine how you could fit this device over the residual limb of someone who doesn't have a hand. And then the cool thing about this is that it's a closed volume of water in this case. And so you don't actually need an air compressor or a pump in order to actuate it. All you need is the end of it. And that could be pulled by a cable that is actuated by the user's own joints. So we did some demonstrations of some of the everyday tasks that we're able to do with this body-powered prosthetic hand. So you're able to write on a whiteboard. My student was also able to pick up a butter knife off the table and use this device to spread cream cheese on a bagel. She's able to pick up a fork and get a slice of banana on it. So it's exciting, some of the everyday tasks that my student was able to do while wearing this. So some of the key takeaways here are that because we have this closed fluidic system, then we can have some of the benefits of like soft fluidic robotics, but with body powered operation. And that we showed that at least some everyday tasks are possible with such a device. So our future directions are that we want to enable grasping of more objects. Right now, it's really hard to pick up a plate with this, and picking up things in everyday life is very important for prosthetic hands. And so we're going to work on trying to adjust the design to make it more versatile. And we're also interested in studying the interaction of this with the human body and thinking about like which joint would it be best to have it being the joint across which the cable goes, so that it at least impacts the other motions that the user wants to do. All right, so that was our body powered prosthetic hand project. And now I want to talk about our soft wrist exosuit. So this project is led by my PhD student Cataline, as well as my collaborator Yasemin. And this is based on this actuation concept of what's called a fabric pneumatic artificial muscle. So this artificial muscle is made of a tube of fabric that is airtight. It's coated in silicone. It's ripstop nylon that's coated in silicone, and it's a woven fabric such that the weave of the fabric goes at a 45-degree angle like this to the length of the muscle. And then it works kind of like a finger trap, where when you inflate this muscle, the whole thing balloons outward and it shortens in length. And so we were interested in using this actuation concept to move the human body. So we built this prototype we started by focusing on the wrist joint. And this prototype of our wrist exosuit has 4 of these fabric pneumatic artificial muscles, one on the top, one on the bottom, one on the left, one on the right, spaced around the user's wrist. And we also have 2 IMUs, inertial measurement units, that measure the orientation of the forearm and of the hand. And the actuators are attached to the human body on one side with an elbow band, and on the other side with the glove. And then these are the off-board components that just contain the pressure regulators used to regulate the air pressure in the system, and then we also have a microcontroller and a single signal conditioning circuit. So some of the cool things about this are that because the actuators are literally just a piece of fabric, the exosuit is super lightweight and flexible when you are not inflating it. So it can kind of just act as like a low profile garment. But then when you actuate it, it's strong enough to move the human wrist in the different directions. So it's moving the wrist there in flexion, extension, radial deviation, and ulnar deviation. And we showed that we can do 3D trajectory tracking with this using the IMUs and using a very simple feedback control law. And we're able to coordinate the motion of the antagonistic muscles to get the wrist to move along this desired trajectory. We also did a lot of modeling to do some design optimization of the design of this so that we could choose the placement of where we should put the ends of the artificial muscles on the body in order to maximize the torque that the muscles are able to exert about the wrist joint, and also the range of motion to most closely match the biological range of motion and torque. Turns out we were able to mostly match the biological torque, but when you get close to the edges of the range of motion, these actuators max out in their ability to contract. And so we can't actually get the full range of motion and torque as the biological wrist. So that's something that is an area for future research. So some of the key takeaways here are that this exosuit can provide high strength and a lightweight, comfortable form factor. Even though we can't get the full range of motion of the wrist in a large range of motion, we can get very high strength. Some of the future directions are that we're interested in extending this to other joints and kind of using our design optimization framework to figure out the best diameter and placement of these muscles to move, for example, the head and neck or the hip. And we're also interested in exploring use for at-home rehabilitation, because this is a super lightweight system that's relatively low cost that a patient could maybe take home to do stretching exercises while they're not in the clinic. All right, so that's the end of the softer exosuit section. And that brings us to the end of the wearable robots section. So that brings me back to the main thesis of my talk, which is that soft and continuum robots have this immense potential to assist humans with navigation and manipulation in the unstructured environments of the real world. And I'm excited about the future of robotics, where we'll see all sorts of really cleverly designed robots that can help people in all these unstructured environments. So I was asked to talk a little bit about my soft robotics class. So I teach two classes at Notre Dame. One is Introduction to Robotics, and then the other one is a soft robotics class that I developed and taught for the first time last spring. So we cover in the course 7 main topics that each have a homework assignment. So we do an overview of soft robotics, then we talk about fine robots, artificial muscles, variable stiffness, soft robot sensing, soft robot control, and soft robot simulation. I also talked about my philosophy on how to come up with a research project idea and how to start a project and how to communicate it. And then we have some guest speakers, and then the students do a final project where they choose a research question to answer in soft robotics and then do experiments and write a paper about it. So these are some examples of the student final project from this spring. This group did a soft gripper that's actuated with soft actuators, and they were studying the effect of having rigid fingernails attached to a soft gripper. This student was working on a variable stiffness mechanism using layer jamming that can change the stiffness of a robot joint. This student was working on an optical waveguide that can sense stretch and bending of this silicone piece. And then this student was working on a new sheath for a McKibben artificial muscle actuator that is actually crocheted, and she found that with different crochet patterns, you get different directions and amounts of helical bending when you inflate it. So this was a really fun course and a great opportunity for both me and the students to learn about soft robotics and some of the cool designs that are possible with soft robots. All right, so that's the end of my talk, and I'd be happy to answer any questions. Yes.
Yeah, so I have a question about the spider monkey inspired robot. So you have some stiff joints, then you have some rubbers around them. So I'm wondering, what about just use a piece of soft material like a silicone thing? Would that achieve the same effect or would it not?
Yeah, great question. Here, I think. So, yeah, so you were saying, why not, are you saying why not have the whole thing be made of silicone?
Yeah, so like there's kind of robot that's based on the causal rat model,
Yes.
right? And then it's just with a lot of plate and it's gonna be something similar, or is it completely different?
Yeah, so we were really trying to get a robot that would be strong, but also adaptable.
Mhm.
So we were thinking that it would probably be good to have this rigid structure inside of the robot to
Mhm.
give it some natural strength.
Mhm.
Because from my experience with vine robots, they're hollow inside and they're not very strong in bending.
Mhm.
So with this design, we wanted to have it mostly be rigid, but just have that softness to make it adaptable to different sizes of objects and that it could grasp.
Okay, sounds good.
Yeah.
I have a question regarding the wine robot. So once you, after you inflate it, if you want to like again retract it, do you just deflate it and roll it back, or can it again get back to its position?
Yeah, that's a great question about vine robot retraction. I think I've got a slide on that here. Yes, so I actually worked on that during my PhD, and it turns out if you want to try to retract the robot and get it to ungrow, one of the ways, if you just deflate it, it's not going to work. It's going to just vacuum down. And so what you have to do is pull back on that inner material. But if you pull back on it from the base using this spool, a motorized spool, the robot tends to buckle into this uncontrollable shape as is shown in this top image here. So here we're trying to pull it back in, but it doesn't actually go in, it kind of slides around. And then it eventually goes back in after you get back to the base. But in many applications, that's not desirable. This is an example where you're growing over an environment with tape on the bottom of the robot, and you're trying to take samples of the environment by like folding back in the soil that you've covered, and it doesn't work if you just retract it from the base. So what we did was we put this retraction device here that is very similar to the propulsion device that I showed you for the inverting toroidal robot. And it actually pulls in the material from the robot tip, and it turns out that works to allow it to retract nicely, and you can use it in this example to take samples of the environment. Yes.
Could it have variable diameters? Like, so could you have like a thin part and then like, I'm imagining, so like someone's trapped underneath, so you have the thin part and then like expands to like a huge balloon or something?
Yes, you can. Actually, there's a video with that on the Veritasium YouTube channel. You should look it up. It's a great 15-minute video all about vine robots, and I'm featured in the middle of it. But they have a demo where they grow a vine robot, and it has, at the end of it, it has like a pillow that grows out, and it can inflate under something and lift it. Yeah. Yes.
You know, if anyone's tried filling them with helium, like to try to get it to lift.
Yeah, that's a really good suggestion, because then you wouldn't have to worry about the weight of the robot collapsing itself. No one has done helium that I know of, at least there hasn't been a paper about it. But I think it's definitely an interesting idea. And there have been other really long inflatable robot arms that have been filled with helium. I can send you the paper, one paper that I'm thinking of if you want later on. Yes.
Yeah, so I'm pretty intrigued by the optical sensors. And the strain based on the animation that you show seems pretty okay.
Yeah.
So have you tried to estimate force based on the strain? Because the force sensor that you show seems to just add a lot more variability because of the size of the area that it touches, but if you do have a model of the robot, like the collapse model, right?
Yeah.
You can kind of calculate the stress or the force on it, or is it just not accurate?
Yes, so you're asking about, could you put this sensor onto the Viner bot and then use that to measure the force?
Yeah,
Yeah, I love that idea. That's something that we would love to be able to do, like for this example, I guess. You could think about like touching, if you were to touch the robot over here. Or maybe you touch it right where the sensor is,
Exactly.
that sensor would indent locally.
yeah.
And then you would know that you had to be touching it. So, yeah, I think that'd be definitely something that we should look into. We were thinking about doing that, where maybe we wrap this sensor like helically all the way around the robot. And that way you have the large area coverage of the whole surface.
Hmm.
So yeah, we're very interested in doing that for sure. Yes.
Can you talk more about the math of how you're going from the strain readings to these plots?
Yes. So I'm trying to think if I have a slide on that. I think probably the best one is just this one. So we've got the 3 fibers here. And if you consider each slice through the fiber, it looks like this. And you have in each slice, you have a strain measurement. So you know the strain here, here, and here. Let's say you get a measurement that it's like 10 microstrain here, 0 microstrain there, 0 microstrain there, then you know. But I guess if it's positive, then that means it's stretching its intention. And so then you know that it must be curving that way. What we do is we, let's say you had 20, 10, and 10. We actually just subtract it off and we get 10, 0, and 0. And then you know that it has to be bending opposite the one that's stretching the most. I don't know if that was answering your question or not.
So at local intervals of 0.6 millimeters,
Yes,
you get
you get a local curvature measurement.
curvature and I guess torsion from that as well, or?
We don't get torsion here because we only have 3 fibers and we need, you're right, if we were measuring local curvature, we really only need 2 fibers. But we use 3 because that way we can subtract off any like temperature effects. But in order to do torsion, you would have to have a fiber that's wrapped like helically around your whole bundle. We're not doing that yet, but we might end up needing to. If we can't figure out a way to constrain this so that it doesn't rotate along the body, along the length of it.
Okay. And then to get the global thing.
Yeah, so you-
cross it and then,
So you add up the curvature, we're assuming locally circular, between every sensor measurement along the length, we assume that it bends with constant curvature to calculate the full shape. Yeah.
Yeah.
Yes,
So is there any other sensors that you have tried to measure the full body strain?
full body strain,
Yeah.
like the full body shape.
Yeah, yeah.
Yeah, so I actually worked using IMUs during my PhD. Let me show you, I think I've got a video of that. Where we put IMUs along the whole body of the robot. Yeah, so here with this project, we put IMUs on these sensor bands. We put them every like 3 inches along the body of the robot. And then based on a simple model of how the robot bends between the bands, we were able to back out a full shape of the robot and have some results on this one. Yeah, so this is our video showing the reconstruction of the robot's shape as it goes through this maze. And it actually worked pretty well, where I think if I jump to the end of the video, yeah, here, so this was the ground truth shape is in red that we measured just from a camera. And then the blue was the shape estimate using the IMUs. And we ended up with 9 centimeters accuracy over, or 9 centimeter error over like 100 centimeters deployed length. So it's about 9% error, which is actually quite good.
Mhm. That's cool.
Yeah.
in the the archaeological scenarios where you were steering something at the tip of the robot.
Yes.
How are you communicating with that?
How are we communicating with how are we controlling the steering? We were actually steering the whole body of the robot along its full length. I guess maybe I'll go back to that video where, let's see. So in this video, right here, sorry, the next section is showing the steering. So with this steering mechanism, we put, so in this video, the base is all the way back here and the pressure regulators are actually back at the base, and they put in air through the actuators that run all the way from the base all the way along the full body of the robot. And so it's kind of cool that it worked out that even though we're commanding the entire body of the robot to bend, really mostly just the tip ends. And that's because of the structure of the robot where it's lighter weight to just move the tip than to move the whole thing. And part of this is held in place with some friction with the environment. Did that answer your question?
We're out of time. We have one question maybe you can address quickly. For our last one, have you considered any in-vine mechanism to locally change the turning angle of the vine bots?
The turning angle?
Probably turning, yeah.
The whole body, maybe just locally steer it with like, and there have been actually some devices that do that. And they have like a motorized that can use to bend the angle and to bend the robot locally. And you can actually get much higher curvatures than you're capable of with this type of actuation. So that's also a possibility.
Let's thank Margaret one more time.